Here in section 7.6, we're going to look at integration using tables. And the tables that we're referring to here are the tables that are located in the front of your textbook called the formula sheets, which you can also locate in the electronic version of the textbook on WebAssign if you don't have a hard copy of the textbook. And the tables contain a list of 100 or so formulas for integrating. And we'll just look at a couple of examples of how to use those tables. So let's start with an example like this. Here we've got the region bounded by the curves y equals arctan x, y equals 0, which is of course the x-axis, and then the vertical line x equals 1. And then we're going to rotate that region about the y-axis. We want to find the volume of the resulting solid. Okay, so just to kind of maybe imagine this solid that we're forming here, we have the graph of arctan, which will be something like this, from x equals 0 to x equals 1, and then the y-axis is the lower boundary. So it's this region here, and we're revolving around the y-axis. So we're going to be using cylindrical shells to form the solid. So to remind you here, in this case, if we're doing a cylindrical shell, the integral that gives us the volume will be 2 pi times the integral, in this case from 0 to 1. That's the boundaries of the region. The radius would be x times the height of our cylinder, would be given by the y-coordinate of the function, so arctan x dx. So this formula will give us the volume of the solid that we're forming here. And noticing that the integral that we're dealing with is actually in this form that we see above here, I went ahead and I located the formula 92 in our table of integrals. You can imagine that this formula here could be solved using one of the methods that we've already established, but here we just want to kind of look at using this table of integrals to do all that work for us. So now I'm just going to plug the values into our formula. In fact, here we see it's just x arctan x, so really we're just going to use u as x in the formula. Okay, so we get 2 pi x squared plus 1 over 2 tan inverse of x minus x over 2 plus c. But here actually, let's take away that plus c because we're not going to be just finding the antiderivative. Now we're going to evaluate from 0 to 1. Okay, so evaluating it at 1, we'll have 1 squared plus 1 over 2 is just 1 times tan inverse of 1 minus 1/2 minus, and then let's see, evaluating it at 0, I'll have 1/2 tan inverse of 0, which is 0, minus 0, so just 0. And then let's see, tan inverse of 1 we know is pi over 4. And then, yeah, so then that would be our final value. So let's just quickly distribute the 2 pi. So that would give me pi squared over 2 minus pi. In this example, we want to use the table of integrals to find the integral of x squared over the square root of 5 minus 4x squared. And we kind of notice that if I recognize the form matches the form of number 34 from our table of integrals, which looks like u squared over the square root of a squared minus u squared, right? Because we have x squared over the square root of 5 minus 4x squared. Now it's not quite in the form, but we can do a little bit of manipulating it to get it into that form. So the first thing I might do is rewrite it so that it's in the a squared minus u squared form down here. So the first thing I would recognize is that I would need to let u equal to 2x to get it into that form here, because this is like 2x squared. So that's the first thing I'm going to do, is going to let u equal to 2x. So du is 2 dx. We get 1/2 du equals dx. So now it's in the form 5 minus u squared down there. And we got 1/2 du goes in for dx. But now we actually have to do something with the x squared in the numerator. In this case, because we know that u is equal to 2x, x will equal to u over 2. So that will actually be u over 2 squared, which will be u squared over 4. So I'm going to have a factor of 1/4 that we can take out. Okay. Now we see it's in the form u squared over the square root of a squared minus u squared, where in this case a squared is 5. So that means we're going to use a equals the square root of 5. Okay, so now we can use our formula. So we'll have 1 over 2 times 1 over 4 is 1 over 8. And let's see, we'll have negative u over 2. Square root of a squared minus u squared, again that was 5 minus u squared, plus a squared over 2 would be 5 over 2. Sine inverse of u over a, so that's u over the square root of 5. And then one more step to go back to u equals 2x to bring it back to x. So let's see, and at the same time here I'll distribute the 1 over 8. So we get negative u, which was 2x, over 2 times 8, which is 16. Square root of 5 minus 2x would be 4x squared. Plus 5 over 2 times 1 over 8 will be 5 over 16. And then sine inverse of the square root of 2x over the square root of 5. Okay. And in fact here you could even reduce this 2 over 16 to negative x over 8. Okay. But anyway, so we saw here using this form of the integral from the table allowed us to find our integral for an integral of this form. If I were to try and do this one without using this integral, maybe you can consider maybe this looks like a good choice for doing trig sub, right? Because it seems to be in that a squared minus x squared form for trig sub. But here this kind of saves us the hassle of having to do the trig sub, and so we can use the table instead. Let's do another example here. This is going to utilize multiple formulas. We start with something of the form x cubed sine x, which I can use the 84 here in the table as, you know, and with n equal to 3, right, to get the reduction formula here. Notice all this does is it reduces it to another integral with 1 degree lower in the integral. So you can imagine what they're actually doing here is just doing integration by parts. So essentially this integral formula here was obtained by doing integration by parts. And we can in fact do this integral ourselves, doing integration of parts multiple times. But now I'm just going to use this formula instead to kind of work around that. Right, so here using that formula 84 with n equals 3. So n equals 3 here. We'll have negative x cubed cosine x plus 3 times the integral of x squared cosine x dx. Okay, and then this integral would be in the form that's in 85, but with n equal to 2. So again, we could just do parts again here. But here, let's go straight to that formula there. So essentially, this formula is going to be doing integration by parts for us. So here with n equal to 2, we get x squared sine x minus 2 integral of, here with n equal to 2, now this will be u to the 1, so x sine x. Okay, and then finally we're in the form x sine x, which we can use the 82 up here to get the form of that integral. And again, that's all just done using integration by parts if we wanted to work this one out without having to use a table. So it'll be sine x minus x cosine x plus c. Okay, so now I'll just distribute some stuff out. So we'll have plus 3x squared sine x. And then here we'll have 3 times minus 2, so minus 6. And then distributing into there, we'll have sine x plus 6x cosine x. And there we have it. So really what this formula did is it kind of more rapidly went through the integration by parts without us having to write it out. But of course, since we know how to do integration by parts, I would even suggest you try it that way as well. Do integration by parts here, you would have to apply the formula 3 times. Just kind of like how we did it here. We had to apply the formula 3 times, and each time we applied the formula, it reduced the power by 1 degree. So we'd have to do it 3 times to get it completely gone.